Okay, so for the last talk before the lunch break, I'm happy to announce Lüst, who is going to tell us about species, thermodynamics, and emergent strings. Thank you.
Well, thank you very much. And first of all, also thank you very much to the organizers for inviting me to this very great meeting and presenting the talk here today. So the title of my talk are Species, Thermodynamics, and Emergent Strings. Or there's also a subtitle, The Good, the Bad, and the Ugly. So I'd like to explain you now in the course of the talk who are really the good, the bad, and the ugly. Actually, these fellows these fellows are not the good, the bad, and the ugly. These are my dear collaborators in these projects: Ivano, Basile, Niccolò Cribiori, Carmine Montella. And there's also a paper to appear soon, hopefully, with Alvaro Herraiz, Joachim Masias, and Marco Scalisi. So it's well known that black holes are formed by collapse of matter, of particle. And here there's a beautiful picture from the Event Horizon Telescope. What I want to consider today is a correspondence between certain kind of particles and certain black holes. The particles will be noted by species or tower of species, and there's a related scale, the species scale, and the black holes are doomed to be or denoted to be so-called minimal black holes, and they have also, as black holes have a scale, their Schwarzschild radius, which will be then associated with the species scale, as we will see. So here there's a quick outline of my talk. I will first talk about species and the species scale, and this will be, I think, a continuation of the wonderful talk that Irene just presented to us. Then I will introduce minimal black holes and what we call species thermodynamics. I will come to the emergent string conjecture from the bottom up. And then if there's time, I will also tell you a little bit about this paper to appear about the origin of species thermodynamics and the species black hole transition. So this picture, I think, is well known. You have seen it already here in the conference. It shows the quantum gravity moduli space, M phi, and the related infinite distance conjecture. So as it was pointed out by Oguri and Waffa some time ago, if we go to infinite distance directions in this quantum gravity moduli space, which we call delta phi, there should be a tower of light states, which are also often called species, where the masses of these states drop exponentially with the distance, at least in this asymptotic limit. The emergent string conjecture, ESC, is a refinement or a stronger version of the distance conjecture. It was set up by Lee, Lerche, and Weigand in 2019. And it postulates, it says, that the light tower of states, the species at large distances, are either given by light string excitations, string oscillations, or by light Kaluza-Klein modes, which origin from some decompactification limit. And in fact, the ESC has passed many, or I would say all, top-down tests in various string constructions. There are various subtleties there on the way, but I think there's no counterexample from the top-down to the emergent string conjecture. However, I think it is also fair to say that a bottom-up derivation is so far missing. And when I say a bottom-up, is that we don't want to refer to any top-down string construction, but like to get an understanding, say, from general quantum gravity or black hole principles. In fact, there are recent bottom-up arguments. The one about species thermodynamics and minimal black holes, that's the one I will talk today about in the talk. There's a complementary recent paper which is based on the density of states and also on black holes in quantum gravity theories. And of course, there is a vast amount of literature about consistency of string amplitudes, which always have the aim also to show or not to show that the string spectrum is uniquely fixed by consistency arguments of scattering amplitudes. In this context, I like to quote this recent paper, which I find particularly appealing in this context. So now let me come, what is the species scale? I think it should be also known, was also nicely introduced by Irene, namely when we consider a d-dimensional effective field theory of gravity coupled to particles, coupled to species, there's a scale up to which gravity or the EFT description is valid. So the species scale is defined basically as a scale where gravity becomes strongly coupled. And its first definition was given by Dvali some time ago. You can define the species scale in a d-dimensional effective field theory as a d-dimensional Planck mass divided by the number of particles divided by the number of species with a certain power, with the power 1 over d minus 2. So here in species is just the number of particles below the species scale itself. In this definition, it doesn't really matter what is the precise spectrum, what are the masses of the species, but I like to already point out that the number of species in quantum gravity, in particular in string theory, usually depends where you are in moduli space. So it's a moduli dependent quantity. So now with respect to the ESC, there are two kinds of species, as I've already mentioned, namely the Kaluza-Klein species, which arise from a compactification on a p-dimensional compact space. And then it's not so difficult to determine the number of species in terms of the reference mass, in terms of the Kaluza-Klein mass. And it's given by this expression, it's mkk to a certain power, where the number of compact dimensions in the dimension of the effective field theory appears like here. In the corresponding species scale, then can be also expressed in terms of the Kaluza-Klein mass, and it turns out that this species scale is nothing else than the higher dimension Planck mass of the effective field theory in d plus p dimensions. For the other case, you can also define the number of species, it's a kind of effective number of species in terms of the string coupling constant. It's given by gs to the minus 2, and then the associated species scale takes this form, and if you put these two terms together, we will see that the associated species scale is just the string scale of the string theory in question. There's an interesting little observation which I like to point out here. If you take the formulas for the Kaluza-Klein tower, and if you take the limit, then p goes to infinity, basically you will recover, at least from this aspect here, the relations for the tower of string states. So in this guise, this tower for p equals infinity also contains some information of the string tower. In this case, one should identify the Kaluza-Klein mass scale with the string mass scale. And this will be also relevant later on. Now I want to mention two alternative definitions of the species scales, which were arising, I think, more recently. Actually, the first alternative definition, and this is the one which we will heavily rely on, is that the species scale or the species length can be defined as the radius, the Schwarzschild radius of a certain black hole, which we will call the minimal black hole. And then already from this formula, you can see that the entropy of this minimal black hole is given by the certain power of the species scale, namely by lambda species to the 2 minus d. It's just the normal area law for the entropy of black holes. Another definition of the species scale, I think set up by the Harvard group, is the scale where the higher curvature operators in the effective field theory become relevant. So if you made an expansion of the effective field theory in terms of, say, higher derivative operators, in terms of the curvature, in terms of the Riemann tensor, you can define the species scale also in this way. In this way, I prefer to call it not the species scale, but I prefer to call it lambda UV. But I think in because of some general arguments, you would expect that lambda UV as defined here is always at least parametrically the same as the species scale. However, as we will see, there can be also subtle differences, which I will mention later on. But in several cases, one can indeed show that the minimal black hole radius agrees with the UV cutoff scale, so that lambda UV is basically identical to lambda species. This was done in the paper by Kumon Wafer et al. And also in our work. It's when one considers 2a in a color Biao. In this case, one can define or can identify the number of species with the topological partition function F1, which arises in this context. Another nice instance is 2a and M theory in 10 or 11 dimensions. That was already mentioned in Irene's talk. In this case, one can also compute the species scale by this formula. I think I have a typo here. It should be something like e to the minus lambda over 2. And in fact, one can indeed see the two emergent string limits. One limit where lambda is big refers to the limit of decompactification to 11 dimensions, and the other limit where lambda is small refers to the string limit where the string oscillators become light. And there are also further additional arguments in this recent paper, and together with some other collaborators, with Jose, Matilda, Yishuan, and Ankel, we are trying also to provide further evidence for the agreement between lambda UV and lambda species. It's coming from the minimal black hole definition. So next, I like to consider a little bit more details minimal black holes and what we call species thermodynamics. Species thermodynamics is a notion which we have proposed during the last year. And we like to start with a general Schwarzschild black hole in the effective little d-dimensional theory. And as you know, mass, temperature, and entropy of Schwarzschild solutions are related in this way. The entropy is given by the d minus 2 power of the radius. That is a famous area law. You can also relate it to the mass of the black hole. In this way, the temperature of a black hole is inverse to its radius, and there's also this relation between the entropy and the temperature. And in fact, all these relations basically stem or are consistent with the first law of black hole thermodynamics, that the mass or the differential of the mass of the black hole is given by TdS, or 1 over T is the derivative of the entropy with respect to the mass. I can show this for a particular kind now of a species, the KK species. So let us briefly have a look what is happening if you follow the radius of a certain black hole starting from large radii going to smaller radii. So we start with a large black hole here with large radii, and this is the relation which I have written down here between the entropy and the radius in little d dimensions. We can also follow the red curve all the way along until we hit the species scale, where the radius is in fact given by the inverse of the species scale. And that is precisely the point which we call the minimal black hole, where the Schwarzschild radius agrees with the inverse species scale. Of course, for KK, for Kaluza-Klein compactification, there is in principle also the higher dimensional picture depicted here by the blue curve. And this is happening when the d-dimensional entropy, the little d-dimensional entropy, is the same as the capital D-dimensional entropy. And in fact, as it was pointed out recently also in a nice paper by Bedroyer, Wafer, and Wu, this is just the point where the so-called Gregory-Laflamme transition takes place. We also had some comments in a recent paper with Ankodoki and Antonialis on that. But what I want to do in this case, in this talk, I want to stick to the little d-dimensional description, and basically I want to follow the red curve and define the minimal black hole all the way down to the species scale without, in a way, reference to the capital D-dimensional description. I have also some equivalent pictures here, the entropy in terms of the temperature. I think this is equivalent. Again, we can define the minimal black hole where the temperature of the black hole agrees with the species scale. And maybe without further explanations, two more pictures where I have depicted the radius versus the mass. The minimal black hole is where the mass of the black hole, one can show it's given by the 3 minus d power of the species scale. And finally also plot the temperature versus the mass. Okay, so I think hopefully it is now clear what we mean with the minimal black hole. It is the smallest possible black hole in the effective little d-dimensional theory in the presence of species. In this observation, we will now take as a definition of the species entropy. We will now like to consider basically the species not anymore a priori at least related to the black hole. We want to define entropy also for the species, but we do it via the minimal black hole. So the definition of the species entropy is the definition, we define the species entropy just to be the same as the entropy of the associated minimal black hole. So again, it's the species scale, the species length to the power d minus 2. And similarly, we define the species temperature as the temperature of the minimal black hole. And if you remember my previous formulas, this is just given by the species scale itself. So you can take these two relations, if you wish, as a definition of the species entropy and of the species temperature. But for having really a black hole interpretation, we also have to require that species entropy and species temperature follow the known laws of black hole thermodynamics. So there's more to say. There are more equations, relations to be satisfied just as beside these two definitions. So before we come to this, there's a small remark I'd like to make before. The introduction of the species entropy also goes along with the so-called black hole entropy conjecture. Namely, one also now understands that in the limit of the large species entropy, there should be also a tower of light states, precisely the species we are talking about themselves. So again, if you have this picture of the moduli space, if you go to infinite distances, we have the massless tower of states, the massless tower of species, which we had before. And this goes along with a limit where the number of species grows, becomes large. The species entropy also becomes large, and the species temperature, also with certain fall-off parameters, goes to 0. So this all should happen, indeed happens in the large distance limits in the quantum moduli space. Okay, so let us come back to species thermodynamics. And as I just said, in order to give a consistent picture, the species, the thermodynamic laws must be fulfilled in order for the black hole species correspondence to work. So here are these two relations which you have already written down before. But there's a third relation, namely the relation which is the same relation expressing the mass of a black hole in terms of its entropy or in terms of its temperature. So there's the relation that the species energy, and I will show you how we define the species energy in a second, that the species energy must be also proportional to the mass of the associated minimal black hole. And as I've briefly mentioned, this is nothing else than the species scale to the power 3 minus d, and you can write this also as n species times the species scale itself. So this is an additional condition which we like also to have satisfied in order that the species really follow the law of the corresponding black hole thermodynamics. And as I will now discuss, this requirement will now provide some evidence, some bottom-up evidence for the emergent string conjecture. So let me come to this point. This is based on the paper which we have written last fall with Ivano, who is here, and it's Carmine, our very good PhD student. It's based on the species minimal black hole correspondence. And to make it more sharp, I will not go to any of the details. We can consider the minimal black hole is a kind of a bound state of species. In fact, this goes back also to earlier work of Dwali and Gomez and also myself. And in fact, which I will also discuss later on, there should be a transition between the species and the black hole description as a certain energy scale. So here we have the picture of the species. There's a typical tower mass, and there's the UV scale, the species scale on the one hand, and on the other hand, we have the minimal black hole, which is considered as a kind of a bound state of the species. But the question is now, are there restrictions on the form on the tower? Can any tower, like for example, Dwali had in mind some 20 years ago, form a minimal black hole, or are there certain restrictions on the form of the tower? So the question is, what towers can build a minimal black hole? For that, I like to make a general ansatz for the mass spectrum. I assume that the tower masses are given by this formula with some function f of n. I assume also some particular degeneracy d of n. And without going into the details, you can then get the species scale as the highest particle, so to say, in the tower, which we say it is given by m sub little n. The species number is just summing over all the particles in the tower, and the species energy is basically given by summing all the individual masses of the particular species in the sense of dealing with a microcanonical ensemble. In the same sense, we will also compute the species entropy as a microcanonical entropy of this particular ensemble. I told you I cannot give you all the details, but now I can show you the solution, and the really good solution now, which are the good, is a tower of the following form. We assume first constant degeneracy, then we get a recursive formula, and this recursive formula will at the end tell us that the spectrum of the tower has to have the form, has to have a polynomial form of the form n with the power 1 over p, where p is also restricted. P has to be bigger or equal than 1, and it's also related to this particular constant gamma, which I have shown you in the energy relation before. So this is the good solution of the species thermodynamics requirements, and maybe you even recognize or remember the previous formula of the Kaluza-Klein spectrum, because this solution is nothing else than the Kaluza-Klein spectrum, which I have introduced before already, so to say, from the top-down point of view. So I recall these formulas. We get as a solution back the Kaluza-Klein spectrum, and you can also check, or if you look at our paper, that all the required species thermodynamic relations are fulfilled. So this is a good tower, which we will call a good tower. And moreover, this is a KK tower for finite values of p. However, as I have already mentioned before, you can take also the limit of p equal to infinity, and then this tower looks like a string tower, and you could even say that in this way we have even captured both kind of species predicted by the emergent string conjecture, the Kaluza-Klein species on the one hand and the string species on the other hand, but I will come back to the string species in 1 minute. So if you wish, you could already conclude this is already good evidence for the emergent string conjecture. Let me next give you very briefly an example of a bad tower which does not fulfill the requirement. So these are the bad guys. And only very briefly, it's a tower with exponential degeneracy. The spectrum in the species scale, the would-be species scale, has this form. It's an inconsistent tower that cannot correspond to a minimal black hole for all values of this parameter A and beta. the main reason is because this vector becomes more and more sparse near the species scale. And actually, for consistency, the opposite is required. And you can also, for example, look at the case where A is 0 and the mass is also 0, which is a tower, for example, which would get for a gauge group, U1 gauge group of infinite or very large rank. This is not possible. This cannot emerge in an infinite distance limit. And I think this is also another way to see why rank of gauge groups are consistent in quantum, are restricted in quantum gravity or in string theory. Finally, let me also comment very briefly on the string tower. Again, we call it the ugly case, but perhaps we should not call it the ugly because we all like string theory. Maybe we should call it better the stringy tower. This is a string-like picture, a string-like tower with some exponential degeneracy and a spectrum like this. And here, indeed, and this is why it is called ugly, a little perhaps unpleasant surprise appears because you see that the species scale is indeed given by the string scale. However, there's a logarithmic correction to the string scale, which appeared already also in other instances. So here we see a kind of deviation between the species scale defined like this and the species scale possibly defined by the lambda UV scale by the higher dimensional operators. And also you see that the energy gets these unpleasant logarithmic corrections, which we, in a way, are still a bit unsecure how to deal with. But this is how it comes out. If you accept the logarithmic correction, you would also categorize these as a good tower, but still I would label it as a yellow tower, as an ugly tower. So this table very briefly summarizes the three cases: the good, the bad, and the ugly. The good passes all the thermodynamic tests, the bad are excluded, and the ugly passes thermodynamic tests, however, with some extra corrections which appear at the first sight unexpected. So in the last 1 or 2 minutes, I'd like to tell you very briefly about the new project we are doing right now, because I think this species thermodynamics is really still largely based on black hole notions, and it would be nice to get back these relations from a purely field theoretic perspective. And this is actually what we want to do now. We want to show how, from a field theory perspective, starting from an ensemble of particles, how in a certain limit the expected extensive law for the entropy turns into an area law. So I will not give you all the details. We start from an EFT entropy of an EFT at a certain temperature, where the entropy scales with the volume of a certain box. In addition, because we deal with gravity, one has to apply also the covariant entropy bound, and then indeed, without any details, one can show that in a certain limit, namely that for high temperature, the extensive entropy turns into an area law. And in fact, as we will also discuss in this paper, in this limit, the species will collapse into a black hole. There will be a transition, which we call lambda BH, and maybe one should be careful, because in a different paper by Kumon et al., lambda BH means something different. Here, lambda BH is the mass scale, the energy scale, where the transition from species into black hole occurs. And in fact, this is always parametrically larger than the species scale itself, at least for d bigger than 3, so there's a hierarchy of scales. In fact, this species black hole transition is known already for some time by the work of Horowitz, Polchinski. It is known that there's a transition between string states and black holes, and it's also known that this transition happens at a scale, the string scale over gs square, and you can easily check that it's precisely the scale which we also predict for the mass of the minimal black hole. And to generalize this, one can also now assume or predict that there's also a transition between not only strings and black holes, minimal black holes, but there's also a transition between Kaluza-Klein species that collapse and also form a black hole at a certain scale, which is in a way depicted in this picture. So I can now basically come to my conclusion. There are many things about species and species scale which I couldn't talk about, which are also very interesting for phenomenology, in particular the hierarchy problem, the cosmological constant problem, which is called the dark dimension scenario, where species really play an important role, and also species play an important role for a possible explanation of dark matter particles in the universe. Today I talked more about the fundamental importance of species in quantum gravity. Just to recall, there is a correspondence picture between species as particles and species as minimal black holes. There are strong constraints on the form of the species tower, and they hint toward to the emergent string conjecture. I like to emphasize these thermodynamic bounds are in a way rigorous. Maybe they are not totally complete, but they are at least rigorous and systematic. And I think it would be also nice to compare these bounds on the restrictions of the spectrum, also around the Hagedorn temperature, from results of string S-matrix calculations. So thank you very much.